Swayam Prabha. Digital India. Educated India.
Good morning and welcome to the lecture number 28 of the course Stochastic Hydrology. If you recall, in the previous lecture, that is the lecture number 27, we discussed essentially the construction of probability paper, specifically the normal distribution paper, which we construct by graphical method, and in the lecture previous to that we also discussed construction of probability paper by analytical methods, in which we considered the exponential distribution and then constructed the graphical probability paper. What is it that we use the probability papers for? Let us say that you have the normal distribution probability paper and you want to examine whether the observed data that you have, let us say stream flow at a particular location or rainfall, seasonal rainfall at a particular location and so on. The hydrologic data, you would like to examine whether that fits normal distribution or not. If you plot the data using the plotting positions on the normal distribution probability paper, and if it plots as a straight line, then at least it should plot as nearly a straight line, it should be acceptable as a straight line. Then you can reasonably assume that yes, it fits the normal distribution. What we will do in today's lecture is that we will carry this further and then look at some statistical tests that are available also for examining whether the sample data that you have, observed data, can be assumed to follow a particular specific distribution or not. So, in the previous lecture we discussed the graphical construction of the probability paper, and specifically the normal distribution is what we discussed, and we also introduced the plotting positions that we use for plotting the data on the probability papers, and I enumerated a number of plotting position formulae, but we also saw in the previous lecture that the Weibel's formula, which is given by P is equal to m divided by n plus 1, that gives you, that is the most widely used formula in hydrology, where m is the rank when you arrange the data in descending order and assign the highest rank number 1 to the largest value, and n is the number of values. So, m divided by n plus 1, this gives you the plotting position for the particular value x m. We use the plotting position and then plot the data on the probability paper and then examine whether it can be approximated as a straight line. If we can, then we can reasonably assume that the data comes from a sample that follows normal distribution, comes from a population, the sample data comes from a population that follows normal distribution. We now introduce specific statistical tests that we can carry out for examining whether the sample data that we have follows a specific distribution or not. Now, these are called as tests for goodness of fit. That is, we are examining whether the data can be fit to a particular distribution and how well we can fit that data to a given distribution. So, it is called as a test for goodness of fit for fitting probability distributions. What I mean by that? If you have observed stream flow data at a particular location and then you want to do all the analysis that we have discussed earlier. So, the first step is that you would like to fit a particular probability distribution to that data. So, how well this data fits a specific distribution is the question that we would like to ask. Let us say that you are considering a candidate set of probability distributions, let us say normal distribution, log normal distribution, gamma distribution, etc. So, one by one you would like to try, does it fit normal distribution, does it fit log normal distribution, and so on. So, that you can use these distributions for your further analysis. There are two ways of doing this. One of the ways is, as I mentioned in the previous lectures, use the probability distribution, probability papers. You construct, let us say that you want to examine for normal distribution, you construct the normal probability distribution, which are also commercially available. You can plot the data on the commercially available normal distribution probability paper, and then plot the data as is shown here. This is the data, this is the same example that I considered in the last lecture. You plot the data using the probability positions. So, these are the probability positions as you obtain from the Weibel's formula. And then if you can approximate this as a straight line, that is, this plots as a straight line, nearly as a straight line, then you can say that it follows normal probability distribution. In fact, as you can see from this example, if you are primarily interested in the central region like this, it fits the normal distribution fairly well. Only in the tail regions, either on the high extreme or on the low extreme, it departs significantly from the straight line, indicating that if your interest in fact lies on the tail regions, that is either in the high extreme or on the low extreme, then you should not use, from this result at least, it indicates that you should not use the normal distribution. So, that is the way we use the probability paper to examine whether the sample data indicates that it comes from the normal distribution or any other distribution for which the probability paper can be constructed or is available. The second method is we can compare the observed relative frequency with the theoretical relative frequency arising out of that particular distribution. What do I mean by that? You have the observed data. So, let us say that you have a means of calculating the observed relative frequencies. What do I mean by the relative frequency? Simply n I by n, let us say we put it as P I, which is the probability or the relative frequency n I by n, where n I is the number of values that falls in some class interval I and n is the total number of values. So, this is the relative frequency. The interpretation of probability in our earlier lectures we have seen is in fact it is a relative frequency. So, from the data you have an observed relative frequency n I by n. If the observed data were to fit a particular distribution, then this should be in some statistical sense close to the relative frequency as obtained by theoretically or analytically for that particular distribution. So, that is what we mean by theoretical relative frequency. So, we must have a means of calculating the relative frequency for this particular class interval from the theoretical distribution, let us say normal distribution. So, we for each of the class intervals we should calculate the relative frequency arising out of use of the normal distribution. So, you have on one hand the observed relative frequencies, on the other you have the theoretical relative frequency or relative frequencies arising out of the particular distribution, which also call it as expected relative frequency. By comparing these two, the observed relative frequency with the theoretical relative frequencies, we can conclude in some statistical sense with some confidence, some degree of confidence, that the data that we have can be approximated to follow a particular distribution. Specifically, we introduce in today's lecture two tests that are available, two classical tests that are available for doing this analysis. These are the chi-square test and the Kolmogorov-Smirnov test, both of which use the observed relative frequency and the expected relative frequency. So, we will start with the chi-square test and then go through some details of the chi-square test, and also we will examine through some example, some numerical example, how we actually apply the chi-square test. Remember, the question that we are asking here is that we have a sample, given sample data specifically on stream flows, rainfall, evapotranspiration, soil moisture, etc., which we would like to use in further probabilistic analysis in our models or in our any applications, for which we want to be sure or reasonably confident that we can assume this sample data to have come from a given specific distribution, for example, normal distribution or log normal distribution, etc. So, that is the purpose now. In the chi-square test, what we do is, so as I said, we will discuss these two tests now, chi-square and Kolmogorov-Smirnov test. In the chi-square test, we actually compute the or count the observed frequencies and compute the expected frequency and take the difference and look at what kind of departures we are getting on the observed frequency with respect to the expected relative frequency in some statistical sense. In the Kolmogorov-Smirnov test, what we do is we compute these relative and observed frequencies and take the maximum departure, and based on the maximum departure we conclude whether this can be fit to a particular distribution or not. So, these are the two major tests that we frequently use. We will also discuss some limitations as we progress. So, we will start with the chi-square test. This in most hydrologic applications, chi-square test is very frequently used. As I said, it makes a comparison between the actual number of observations and the expected number of observations. How do we do this? Let us say you have 50 years of monthly data, monthly stream flow values, which means 600 values you have. The 600 values that we have, we divide it into a number of class intervals. Let us say my total range of values is between 0 to 1000. So, 600 values are all within this range, say 0 to 1000. That means 1000 is the highest magnitude that you have in the observed data. We may divide this into, let us say, 10 class intervals, 0 to 100, 100 to 200, 200 to 300 and so on. So, like this class 10 class intervals we may divide, and then look at how many values have appeared in each of the class intervals. So, that is the way we compute the relative frequency. So, the frequency of occurrence of the values in the range 0 to 100, let us say 5 number of times 0 to 100 was occurred. Like this, corresponding to each of the class intervals, we count from the data, we count the number of values that fall into each of the class intervals. So, the steps we will just enumerate now. First is you have to decide whether you want to make this test for normal distribution, log normal distribution, exponential distribution, Gumbel distribution and so on. So, first you decide the distribution for which you want to examine whether the data fits that particular distribution or not. Then each distribution, there is a theoretical distribution, has its own parameters, and we have seen how to estimate the parameters based on the observed data that you have, sample estimates of the parameters. So, let us say you want to examine for normal distribution, you have two parameters, namely mean and standard deviation. So, you get the sample estimates of these parameters from the observed data, and then the observed data that you have, you divide it into some number of class intervals. Let us say we call it as k number of class intervals. It may be 10, it may be 15, it may be 5, 6 and so on. So, we divide it into k number of class intervals. Some guidelines of dividing this into k class intervals, I will explain it presently. Corresponding to each of the class intervals, now we count the number ni which falls into a particular class interval I. As I said, 0 to 100 is one class interval. From the observed data, you see how many times it went into this particular class interval. 500 to 600 is another class interval. You again examine how many times it went into class such things. Now, when you do the classification uniformly, it is possible that you may get no values in a particular class interval. That means, that particular class interval may not have been represented in the data at all, which means you may get a value of 0 there. We will see some general guidelines of how to make the classification, so that the test can be usefully made. Then we will determine the probability with which the random variable lies in each of the class interval using the selected distribution. Let us say you are talking about the class interval 100 to 200 and you want to examine the expected relative frequency of a value belonging to that particular class interval when it is drawn from a normal distribution, for example, normal distribution with a mean of mu and standard deviation of s, standard deviation of sigma. So, we know how to compute the probability of a random variable which follows normal distribution to take values between these two values, these two extreme values of that interval, that means 100 to 200. So, we compute that from the theoretical distribution. Then once we compute the probability, remember probability is what? It is a relative frequency Ni by n. So, from this we can compute the expected number of observations that that the distribution leads to for that particular interval. So, this we can get from the theoretical probability that we got from that particular distribution. How do we get? Let us say the probability of belonging to that particular interval 100 to 200 is given as 0.04 or some such thing, and there are number of values of 100. So, 0.04 into 100 which may come to 4. So, like that we compute the expected number of observations. So, there is a observed number of observations in each of the class interval. Now, we also obtain the expected number of observations in each of the class intervals. Then we compute a statistic which is called as a chi-square test statistic from the data. So, I indicate this as chi-square data as the number of observations in each of the class interval minus the expected number of observations in each of the class interval, the whole square divided by the expected number of observations in the class interval I for each of the summed over class interval I is equal to 1 to k. There are k number of classes. So, sum this over all the class intervals. So, this gives you the chi-square data. This subscript data indicates that this is computed from the data. This statistic follows a chi-square distribution which has as its parameters number of degrees of freedom, that is degrees of freedom of k minus p minus 1, where k is the number of class intervals and p is the number of parameters that your distribution has. Say for example, normal distribution it has 2 parameters, exponential distribution it has 1 parameter and so on. So, the distribution for which you are testing, the number of parameters of that particular distribution is p. So, k minus p minus 1 is the degrees of freedom, and we do this test for a certain significance level, which means we are saying that we want to test whether the data follows a normal distribution at 10% significance level, at 5% significance level, which in a sense indicates, in some rough sense indicates 90% confidence, 95% confidence and so on. So, we are able to say that this particular data follows a normal distribution with that specified significance level of say 10%. Now, there is a critical level of the chi-square value which is associated with the degrees of freedom, which is k minus p minus 1. K is the number of class intervals of your data, p is the number of parameters of the distribution, and alpha is the significance level that you are making the test for. So, alpha can be 0.1 if it is a 10% significance, alpha can be 0.1, if it is 20% significance, alpha is 0.2 and so on. So, typically we use 10% and 5% significance levels. Now, these are the critical values. So, you obtain the chi-square value from the data and then examine with respect to the critical value. If the obtained chi-square value from the data is less than the critical value, then you accept the hypothesis. What is the hypothesis? That the data comes from a distribution, data comes from a population which follows a given distribution for which we are making the test. So, we accept the hypothesis that the data comes in fact from that particular distribution. See, the chi-square distribution looks something like this, and this is the chi-square alpha nu, where nu is the degrees of freedom k minus p minus 1. So, we would like to have our computed chi-square in this region. So, any value of chi-square less than this, you accept the test, and any value of chi-square greater than this, you reject the hypothesis for a given alpha value, which is a significance level, and for given nu value, which is the degrees of freedom. So, as I mentioned, it is usually carried out at 10% significance or 5% significance level. The tables for these are available in any standard textbooks on the statistics. So, we use the tables, and from the computed value we just compare it with the critical values of chi-square that are available from the table. The table gives specifically chi-square values for a given alpha and nu value, which we know how to compute. Now, this is how the tables look. Say alpha is 0.995, 95 etcetera. So, typically we will be using 0.1, 0.05 etcetera. So, this is 10%, this is 5% significance, 2.5% significance and so on. And on the other side you have nu, which remember depends on the number of class intervals that you have. Let us say nu is k minus p minus 1, k is the number of class intervals. Let us say k is 10 number of class intervals, then p is the number of parameters 2. So, 10 minus 2 minus 1, 3. So, you go to nu is equal to 3 and associated with that particular significance level, you compute, you get the critical value of chi-square. So, these values are typically available in most textbooks, standard textbooks of statistics. The number of class intervals, now we will come to the basic question of how do we divide it into some number of class intervals, which is good for the test that we are carrying out. You must remember that the test that we carry for the observed data will be quite sensitive to the distribution of values in these class intervals. So, there are some guidelines available. Specifically, if you are interested in the central region of the distribution, let us say it may be normal distribution or log normal distribution etcetera. You are not really interested in the extreme values, but you are interested mostly in the central region of the values. Then you make sure that your central region has a fair representation in the type of class interval division that you do. The central values are more or less uniformly distributed. In fact, one rule of thumb that in most of the hydrologic applications that we use is that each of the class intervals that we have must have at least 5 values, which means you divide your data into so many class intervals that each of the class intervals has at least 5 values, which also means that the class intervals need not be uniform. Like I said, 0 to 100, 100 to 200, 200 to 300, this is a mechanical way of doing it, simply divide it into so many class intervals uniform length or uniform intervals. But when you do that, there may be some class intervals which may have 0 or 1 values, whereas other class intervals may have 20, 30 values and so on. So, you must do this rather iteratively and then satisfy yourself that each of the class intervals at least have 5 values, which means you may have to combine 2 or 3 class intervals, you may have to combine and then bring it to a given acceptable interval. So, the first guideline is that the class intervals that we are using need not be uniform. They can be, and in fact, in most of the applications they are non-uniform, and each of the class intervals, a general broad guideline is that it should have at least 5 values, which means let us say you have 40 years of observed data, 40 years of annual stream flow data, which means 40 values you have. Let us say you divide it mechanically into 8 class intervals, then you may expect that each of the class intervals should have at least 5 class intervals if the observed data in fact is uniformly distributed all across the intervals. But it may so happen that some of the class intervals may have 0 values, some of them may have 1 value and so on, in which case you combine these class intervals, and rather than having 8 class intervals you may just have 5 class intervals, non-uniform class intervals. So, like this you may have to do this in a iterative manner, or just look at the data and then divide it into some of the class intervals. One rule of thumb of how to divide it into class intervals, how many class intervals that you want, is given by 10 plus 1.33 log n, where n is the number of observations. Now, this is just a rule of thumb. Again, you have to examine whether this type of division in fact is satisfactory in terms of you are obtaining at least 5 observations in each of the class interval. Then when we do this test, let us say that we are doing it for normal distribution first, and we carry out the test. How to carry out stepwise, I will explain it presently, but we carry out the test and then let us say it passes the test, that it follows normal distribution. That is, the hypothesis that the data comes from a normal distribution is accepted when we carry out this test. Let us say we progress further and then examine the data for log normal distribution. Let us say it also passes the test for log normal distribution, then gamma distribution, it also passes for gamma distribution, exponential distribution, it also passes for exponential distribution. Like this, if we have the test passing or the acceptability of hypothesis being true for several distributions, 1 distribution, 2 distributions, 3 distributions and so on, then which one do we choose? Look at this critical values of chi-square data. Now, this in some sense indicates the acceptability of that particular statistic as obtained from this. So, you accept the particular distribution, you use the particular distribution which gives the least value of chi-square. That is one general guideline. So, first you divide the data into some number of class intervals, make sure that each of the class interval has a reasonable number, which is 5 number of observations in this particular case, and then make sure also that your sample size is reasonably large. That means, as I mentioned, if you had 40 values and divide it into 8 class intervals, you may expect, if they are all uniformly distributed across the region, then you may expect at least 5 values. Let us say you have only 20 values and then you divide it into 8 class intervals. Then there may be many class intervals which are not represented at all, in which case you may have to combine them and bring it down to 3 class intervals, 5 class intervals and so on. For these tests to be useful, or for these tests to be more reliable, the available data must be large in length. That means, you must have significantly large length of data. If you use this test for just 10 values, 20 values and so on, then your confidence in the results can be quite small, and therefore, any statistical tests of this type, where we are looking at goodness of fit of the distributions, must be essentially done on large length of data. So, let us see how we use the chi-square test for fitting the distribution with a example, and we will take the normal distribution. we are looking at the annual maximum discharge x for 40 years. So, this is the 40 years data. So, this is a serial number and this is the value. It is in cubic meters per second. So, into 10 to the power 6 cubic meters per second. So, there are 40 values now. We want to examine whether this sample of observed data comes from a population that fits normal distribution, comes from a normal distribution. And we will examine this using the chi-square test at 10% significance level. So, as I said, first we divide it into a number of class intervals. Let us say we arbitrarily choose 8 class intervals in this particular case. So, there are 40 values and we choose it as 8 class intervals. Look at the actual range of values and then using your judgment, we will say that less than 400 we call it as class number 1, 400 to 500, 500 to 620, 620 to 740, etc. As you can see, they are not uniformly, they do not have same length. We also compute, because we are talking about normal distribution, we compute the parameters of the normal distribution, or we estimate the parameters of the normal distribution from the sample. So, these are the sample estimate. X bar is 657.42 and standard deviation S is 173.59. Remember, the basis is that we want to examine whether the observed relative frequency or the observed number in each of these class intervals closely approximates the expected number in these in the corresponding class intervals if it follows normal distribution. That is the basis now. Observed relative frequencies we can directly obtain from the data. For example, I know how many of those 40 values are less than 400, how many of them fall in 400 to 500 and so on. So, that is directly from the data. Now, from the theoretical distribution, we must be able to get what is the expected relative frequency of these particular class intervals. That means, if we randomly select a value from this particular distribution having these parameters, then we must know how many times that random variable can take values between 400 to 500, how many times it can take from 500 to 620 and so on. So, corresponding to each of the class intervals, we have on the one hand the observed relative frequency and on the other we have the expected relative frequency, or in this particular case we directly have the observed number and the expected number. So, how do we get the expected number? Expected number is simply, as I said, probability of that particular interval being represented multiplied by the total number, because the probability is simply relative frequency Ni by n. So, Ni can be got as Ni by n, which is the probability, multiplied by n, which is the total number of observations. So, from the theoretical probability you multiply it by the total number of observations to get the expected number. So, this is how we do the example now. We have the class intervals, 8 class intervals, less than 400, 400 to 500 and so on, we have 8 class intervals. The Ni is the observed relative observed numbers. This is from the observed data. So, what I mean by this is that you have 3 number of values which are less than 400. Similarly, 2 less than lying between 400 to 500 and so on. Like this we do the observed data, observed number. Then we compute the z corresponding to the upper value of this, that we call it as f of zi. How do we compute z? This is simply our x minus x bar by s. So, we use the higher value 400 in this case minus x bar 657.42 divided by s, which is 173.59. So, you get a z of minus 1.483. So, this is from the upper limit. What does this give? This gives f of z, capital F of z, which is from this we can get capital F of z, that is from the z you can get capital F of z up to this point. that is probability of z being less than or equal to the given value of z, that is what it gives. From the f of z, you can calculate the probability of that particular interval. For the first value, the f of z itself gives the probability. That means, you are starting from f of z is equal to 0, you are going up to this point 0.069. So, this gives the probability of the value of class interval falling in this particular interval. That is, I will repeat that, the probability that a value randomly chosen will fall in the class interval 0 to 400 is 0.069, that is what you get here. Then from this you get the expected number. So, this is from the observed, you got the observed number, and this is the expected number. So, the expected number, as I said, you will get it based on the probability multiplied by the number. So, n into pi. So, n is 40 here, n is the number of observations into pi, and then you get ni, which is the observed data, minus ei whole square divided by I. Remember here, let us say you go to class interval 2 now. Class interval 2, you have 0.182 associated with this z value. How do we get this? First, you get the z value corresponding to the higher limit of this class interval 500, and then that is minus 0.907. Associated with minus 0.907, you get f of z I, which is 0.182, then f of z I minus f of z I minus 1. So, 0.182 minus 0.069, that is what you will get as 0.113. So, you use the previous two values and then you get 0.113. Once you get 0.113, then you multiply that by your n value, sorry for this, and then you get the expected number of values. Remember here, the expected number need not be an integer, because we are taking it out from a theoretical distribution. So, you will get numbers such as 2.76, 4.52 and so on. So, although we call it as a number, it need not be an integer here, it is just the expected number of values. Now, we calculate ni minus ei the whole square divided by ni, which means in this particular case you have 3 minus 2.76 the whole square divided by 2.76, which is 0.021. Like this you calculate all of this, the sum of that will be 4.448. This is the chi-square value that you obtain from the data. Now, this chi-square value we will so chi-square from the data, I indicate it as chi-square data, is 4.448, which is just the sum of these values. Now, the number of class intervals we have decided as 8, and the number of parameters is 2, because we are talking about normal distribution, mean and standard deviation, and therefore, the degrees of freedom, which is nu, is k minus p minus 1, which is 8 minus 2 minus 1, which is 5, and we are testing it at a significance level of 10%, which is alpha is 0.1. So, we have degrees of freedom of 5 and the significance level of 0.1. We enter the chi-square table and then obtain the critical value of the chi-square. So, this part of the chi-square table is reproduced here. These tables, I repeat, are available in any standard textbooks. So, you must only know how to read the tables. So, for reading the table, you need the degrees of freedom nu, which is calculated as k minus p minus 1, and the significance level alpha. So, we are doing the test for significance level of 0.1, and the degrees of freedom as we obtained is 5. So, associated with 5 of nu and 0.1 of alpha, you get the critical value of chi-square as 9.24 from the table. So, this is chi-square 0.15 comes to be 9.24, and what is our chi-square data? It is 4.448. So, the chi-square data 4.448 is less than the critical chi-square value, which is 9.24, and therefore, we accept the hypothesis that this sample in fact comes from a population having normal distribution. So, that is the way we carry out the chi-square test. We demonstrated the chi-square test with normal distribution. Let us say you wanted to do it for exponential distribution. What is the difference? The difference lies in only the expected relative frequency. How we compute the expected relative frequency? So, we must know how to compute the expected relative frequency associated with any of the probability distributions, which we from our earlier basics of probability distributions we know. For example, exponential distribution, you know capital F of z, f of x, which is the CDF of that, and from the CDF you get probability of x being less than or equal to x, and therefore, between two class intervals, let us say you are talking about 100 and 200. So, you know the probability that it lies in that particular interval if it in fact came from exponential distribution. So, the only difference between distribution to distribution lies in the way we compute the f of z here. In this particular case we call it as z, we can also call it as x if there is any other distribution. We call it as z here because we are relating it to the normal distribution. So, given any distribution, we must know how to compute the expected number that can be comes into that particular interval, and we know how to compute these, because once we know the probability, you know the total number of values, and therefore, you can calculate the expected number of values. So, this test you can do it for any of the distributions like normal, gamma distribution, exponential distribution, etc. All the distributions we know how to compute the capital F of z, maybe from analytical method or maybe from numerical integration methods and so on, the tables for which are available. So, we know how to compute the capital F of z, f of x, which is the CDF value. From the CDF value, we can compute the expected number of values that fall in a particular interval, and then we compute the associated chi-square value, compare the chi-square value that you compute from the data with the critical chi-square value, which depends on the significance level at which you are doing the test, as well as on the degrees of freedom given by k minus p minus 1. Apart from the expected number of values that change from distribution to distribution, the p, which is the number of parameters, also changes from distribution to distribution. Exponential distribution, for example, has only one parameter lambda. So, p will be 1. Log normal distribution will have 2 parameters, gamma distribution will have 3 parameters, and so on. So, we know now how to carry out the test. There is another test that we will discuss now, which is called as the Kolmogorov-Smirnov test. This is an alternative to the chi-square test. Normally, when we want to examine whether the data fits a given distribution or not, we carry out both the tests for reasons that I will come to slightly later. Kolmogorov-Smirnov test is advantageous computationally, and also in many situations it is a superior test statistically. So, in chi-square test what we did is that we compared the relative frequencies with the observed frequencies and then obtained a statistic out of it. What we do here is that again we rather than dividing it into class intervals, we use the data as they are observed and then compute the probabilities of those values occurring. So, here like we did in the probability plotting position methodology, what we do is we arrange the data in a descending order, highest value first and the lowest the last. Then the cumulative probability associated with each of these is calculated from the Weibel's formula. That is, what is the Weibel's formula? It is a small p is equal to m divided by n plus 1. This is what we discussed in the last class. So, small p is equal to m divided by n plus 1. What does it give? It gives probability of x being greater than or equal to x, that is a particular value of x. But we want the cumulative probability, that is f of x is what we need, that is x being less than or equal to x, and therefore, we take 1 minus p of that and then get the cumulative probability associated with that particular value of x I. So, the first difference that we see from chi-square between chi-square and Kolmogorov is in the Kolmogorov test we are not doing classification, we use the values as they are and arrange them in the descending order, compute associated with each of the values the f of x, capital F of x, which is the CDF value, and this CDF value we compute based on the Weber's formula. This gives you the observed cumulative probability, but we also have a theoretical cumulative probability associated with each of the observations. This we get it from the parent distribution, the distribution for which we want to make the test. For example, for the normal distribution we know how to compute the cumulative distribution function associated with that particular value. So, we calculate the cumulative theoretical cumulative probability, and then we take the absolute difference between the observed cumulative probability and the expected cumulative probability. So, this is from the observed data using the Weber's formula we get P of x I, and this is from the theoretical distribution f of x I, and we take the absolute difference, and the test statistic for the Kolmogorov test is denoted as delta. We take the maximum absolute difference between P of x I and f of x I, and this maximum difference, absolute difference, we compare it with a critical value of the Ks statistic. The Kolmogorov-Smirnov statistic is also abbreviated as Ks statistic. So, this Ks statistic delta naught again much like the chi-square test, chi-square statistics, they are available in standard textbooks. So, we can pick up corresponding to a given significance level of alpha. So, delta naught just depends on significance level of alpha. Now, if the delta that you have calculated thus as a maximum absolute difference between the observed CDF and the expected CDF value associated with the value x I, if delta is less than delta naught, then we accept the hypothesis that the assumed distribution is a good fit at significance level alpha. Remember, when we are making conclusions, always you must remember that we are doing it at a particular significance level. Let us say the test fails at 5% significance level, but it passes at 10% significance level. So, it is possible that then you may have a 90% confidence and not 95% confidence that it fits that particular distribution. So, this you must always keep in mind. These tests are associated with a certain degree of confidence that you have, and therefore, they are carried out at that particular significance level. Not therefore, they are associated, the confidence level is associated with the significance level at which you are carrying out the test. Now, the statistic delta naught, which is a critical statistic against which you are comparing your computed delta, they are available in the tables, and this is how the table looks. It is dependent on the sample size. Remember, your chi-square depended on the number of class intervals in terms of the degrees of freedom that you had, because chi-square k minus p minus 1, that is the degrees of freedom, and alpha, that is how your chi-square tables were prepared. But the Kolmogorov statistic depends on the sample size itself. Do you have 40 values, do you have 100 values, 50 values, and so on. So, based on the sample size and the significance level, you can get the Kolmogorov statistic delta naught. These are typically given up to 50 values, and then for more than 50 values, when you have n greater than 50, you have some asymptotic values 1.07 divided by root n and so on. So, if you have more than 50 values, you use these Ks statistic as critical values delta naught. Now, the advantage of Kolmogorov-Smirnov test is, first of all, look at the computations. All you have done is you have arranged it in decreasing order and then assigned the ranks and then calculated the observed observed f of x, which we denoted as capital P of x, and then you also know how to get f of x from the theoretical distribution. So, all you are doing is get the distribution differences P of x minus f of x and then pick up one value out of that. So, doing it is very simple. Also, you do not lump the data, that means, because you were in chi-square test, you were distributing it into some number of class intervals, which means anything that falls between 0 and 100, you are lumping all of that data into one class interval, and then based on this class interval expected frequency etcetera, you are calculating. So, in the Kolmogorov-Smirnov test, you do not do that, you use the observed data as they are. So, that is one advantage. Now, when the sample size is small, the KS test is more convenient to handle compared to the chi-square test. So, these are some of the advantages, and in some statistical sense, the Kolmogorov-Smirnov test is superior to chi-square test in many situations. That means, what I mean by that is, if your Kolmogorov-Smirnov test passes and the chi-square test fails, you may go with the Kolmogorov-Smirnov hypothesis, Kolmogorov-Smirnov test result, and vice versa. Let us say the chi-square test passes, but the Kolmogorov-Smirnov fails, in which case you should respect the Kolmogorov-Smirnov test more. So, we will do the example, we will do an example now. We will take 20 years of data and then look at how we carry out the KS test. Now, these are the data values. First, we arrange the data values. I will explain everything through one table. We want to carry out the KS test at 10% significance level to examine whether this particular data can be assumed to follow a normal distribution. We compute the mean and the standard deviation, because we need it for calculation of f of x, capital F of x, because we are following normal distribution. Because it is normal distribution, we need these two parameters. Then we arrange the data in decreasing order, and associated with each of the value, we first calculate p, small p, which is probability of exceedance. Remember, x is greater than or equal to x m, associated with that particular rank m, and then from p we can get the CDF value, which is 1 minus p, and then associated with this particular value of x, we can also get the z value, and therefore, we can get the expected f of x, capital F of x. So, that is what we do. Now, this is I is equal to 1 to 20, there are 20 values. These are the x values, which are the actual available data series. We arrange this data in descending order. So, this is the descending order series, 895 highest, 831 and so on. We assign ranks 1, 2, 3, 4 etcetera. Highest value gets the rank number 1, the lowest value gets the rank number 20. We calculate the Weibull probability, p is equal to m divided by n plus 1, m is the rank here, n is the number of values, which is 20. So, we calculate all of these values. Then we get the observed f of x, observed CDF, which we denote it as capital P of x of I, which is simply equal to 1 minus p. Why? Because p is the exceedance probability, and the CDF gives you probability of x being less than or equal to x, and therefore, the CDF value is 1 minus p as obtained. So, we get these values like this, and then we get the Zi corresponding using this equation, x minus x bar or s. So, for example, this is x minus x bar that we have, which is 619.62 divided by 153.32. So, that is how we get Zi. Once we get Zi, we know how to calculate f of Zi. You go to the tables and get the f of Zi. So, you got the expected probability and you have the observed probability. You take the absolute difference between these two, 0.952 minus 0.964, which will be negative, but you are taking absolute values. So, these are the absolute differences. When you get these absolute differences, look at the maximum absolute difference. This is 0.056. This defines the delta, which is the Ks statistic. So, the maximum value is delta, which is equal to 0.056. We are doing the test at significance level of 0.1 or 10% significance, which is 0.1. Our sample size is 20. So, we go to the Kolmogorov-Smirnov table, statistic table, associated with n is equal to 20 and alpha is equal to 0.1, we pick up the value 0.26. So, delta naught is 0.26. The observed delta value or delta value coming out of the data is 0.056 and the critical value is 0.26. Because this is less than delta naught, we accept the hypothesis. So, the hypothesis that the data comes from a population following normal distribution is accepted at 10% significance level when we follow the Kolmogorov-Smirnov test. Now, there are two goodness of fit tests that we discussed. One is the chi-square test and another is the Kolmogorov test. When we are dealing with the middle range of the observations, let us say you are talking about monthly stream flows and then you want to plan for a reservoir for water supply and so on. So, essentially you are interested in the middle range of the sequence or middle range of middle values of the distribution. These tests are quite useful, but the moment you go to the extremities, extreme values, and then you want to examine whether these extreme values follow a particular distribution or not, then these tests are not really very useful. In fact, many hydrologists discourage use of these tests when we are interested in the extreme values. Also, when the sample size is small, probability of accepting a hypothesis when it is in fact false is quite high. So, you must be alert to the situation where your sample sizes are small and when you are dealing with extreme values. So, these two limitations you must keep in mind, especially in applications in hydrology, before we mechanically apply these tests and then conclude that it follows a particular distribution or not. So, in today's class then we examined specifically two tests, which is chi-square test and Kolmogorov-Smirnov test, both of which are used to examine the hypothesis that the data that we have comes from a population fitting a particular theoretical distribution, normal distribution, log normal distribution, etc. So, the specific exercise that we did today is to use these two tests to examine whether the data comes from a normal distribution, and these type of examples exercises are necessary when we want to fit the data to a particular distribution and then start using all the methods of analysis that we discussed earlier on. Because subsequently once we assume that it is a normal distribution, we know what is to be done with the normal distribution and so on. There are however limitations of using these tests. If you are interested in the extreme values, we must be cautious in using these two tests. Also, the Kolmogorov-Smirnov test in many situations is a superior test compared to the chi-square test. When the sample sizes are small, these tests should be used with caution, and these tests can complement the probability paper test that we have discussed earlier. That means, you use the data and plot it on the probability paper for that particular distribution, and maybe you also use the chi-square test, Kolmogorov-Smirnov test, etc. so that your confidence in the hypothesis that this comes from a particular distribution is quite high. So, in the next lecture we will move on slightly further away from the fitting of the distributions. We will see how we use all of this information in hydrologic designs, specifically starting with the intensity, duration, frequency relationships, etc., and then going on to the design stuff. Thank you very much for your attention.